Welcome to the Language Year, Comprehensible Input for Learners. Today we're doing a deep dive into a name that feels, well, almost mythical in science. Isaac Newton. We hear his name everywhere, right? But the real story, the man behind the legend, it's even more fascinating and honestly full of surprises you might not expect.
It really is. When you think of Newton, it's probably gravity, maybe some complicated equations,
Hmm.
but understanding his life, his journey, and just the incredible depth of his mind, it gives you such a richer picture.
And that's exactly what we want to get into in this deep dive. We've got some great source material here, and we're going to try and pull out the most important bits, the key insights. Our goal, as always, is to make even the trickier ideas simple and clear, whether you're learning English or just really curious about one of history's biggest thinkers.
Yeah, it's a chance to kind of peek inside the mind that truly shaped how we understand the physical world.
Okay, let's unpack this then. His story starts with, well, difficulty right from the get-go. He was born prematurely, Christmas Day, 1642, just a few months after his father had died. He was so frail, apparently, people didn't think he'd survive even his first few hours.
A really challenging start,
Yeah.
absolutely. And his childhood didn't get much easier from there. When he was only 3, his mother remarried and moved away, leaving him with his grandparents for, about 8 years? That separation definitely played a part in him being quite solitary, quite introverted early on.
Yeah, you can see how that would shape someone. Apparently, he wasn't the most social kid at King's Grammar School in Grantham. But there's that story, isn't there, that shows he had this surprising inner toughness, standing up to a bully.
Yes, exactly. He might have been quiet, but clearly had a defiant streak when pushed. And while he was lodging in Grantham, he stayed with a Mr. Clark, who ran an apothecary shop. Being around that environment seems to have fostered an early interest in mechanics, even things like potions. He found a real refuge, it seems, in building models like kites, water clocks, using ideas he found in books. It was sort of a way to escape and explore things on his own terms.
Right, so from that rather solitary, mechanical kind of childhood, he heads off to Cambridge, Trinity College, in 1660. But he didn't have much financial support from his mother, did he? He had to work his way through.
That's right. He was a subsizer, basically doing chores, menial tasks to pay for his education.
Yeah.
And he stayed largely solitary there too, kind of observing others from a distance while he socialized. But this is where his intellectual world just exploded.
What sort of ideas opened his mind there? What was he encountering?
Well, he was getting into the cutting edge, thinking of the time people like Descartes, his ideas about how the universe worked mechanically. Even strange concepts like planets being carried along by invisible swirling matter, vortices. And crucially, through Isaac Barrow, the mathematics professor, he discovered the work of Galileo, Kepler, and especially Descartes' powerful algebraic methods.
And math just clicked for him instantly.
Well, it was more than clicking. It was like a revelation. He just threw himself into it, taught himself pretty much all the major advancements in mathematics from the previous decades.
Yeah.
It was during this intense period of self-study that he really realized just how extraordinary his own mathematical talents were.
Okay, so here's where it gets really fascinating. Just as he's hitting his intellectual stride, the plague arrives in 1665. Cambridge University has to close down, and Newton goes back home to his family's farm in Woolsthorpe.
And this period, roughly 18 months, becomes one of the most legendary episodes in the history of science. His year of wonders. Working almost entirely alone without university resources, he makes incredible breakthroughs simultaneously in math, in optics, and starts thinking really deeply about gravity.
It's kind of hard to imagine one person doing all that, mostly in isolation. But the sources mention he wasn't exactly rushing to publish all this.
No, not at all. That was a strong part of his personality, especially early on. The sheer joy and challenge of the intellectual work seemed to be enough for him then. He wasn't driven by immediate fame or publication. It's a decision, though, that he'd later come to regret when priority disputes flared up.
Right. Which brings us nicely to his mathematical revolution. He developed the foundations of calculus, calling it his method of fluxions and fluents.
Hmm.
Man, for someone who isn't a mathematician, how can we get our heads around what this revolutionary tool actually did? What did it unlock?
Well, think of it like this. It gave mathematicians and scientists a way to analyze and predict things that are constantly changing or moving. Before calculus, you could figure out the average speed of something, say, a cart rolling down a hill.
Hmm.
But figuring out its exact speed at one specific moment, that was incredibly difficult.
Ah, okay. Dealing with things right now, the instantaneous stuff, even if right now is just a fleeting instant?
Precisely. He thought of quantities like distance or maybe temperature as things that flow or change continuously. he called these fluents.
Hmm.
And the rate they were changing at any given moment, that was the fluxion. It's basically analogous to the modern idea of a derivative, the instantaneous rate of change. He even had his own notation using a little dot over the variable.
So fluents are the changing things. Fluxions are how fast they're changing at that instant.
Exactly. And he also worked out the inverse process, figuring out the total change, or maybe the area under a curve, by essentially reversing the process of finding fluxions. This unified way of looking at change and accumulation was just incredibly powerful. It gave scientists brand new tools.
And this is where that famous priority dispute with Gottfried Wilhelm Leibniz comes in, right?
Yes, the big controversy. Newton definitely developed his core calculus ideas earlier, back in the 1660s during that Year of Wonders. But Leibniz, working independently over in Germany, developed his own version of calculus, and crucially, he published it first in 1684. That was years before Newton put his own definitive work out there.
Oof. That sounds like a recipe for conflict.
It absolutely was. The dispute got very, very bitter, fueled by national pride, supporters on both sides piling in. Newton, especially later when he held a lot of power at the Royal Society, fought tooth and nail to defend his claim to being first. He even, well, influenced the official report that ultimately concluded he was the first inventor.
And there are different ways of writing it down, the notation, that became part of the story too.
It did. Newton used his dots for fluxions, while Leibniz used the dx and the Nicobaeus symbols we mostly use today. Leibniz's system just turned out to be more flexible, easier to use, really. It spread quickly across Europe. British mathematicians, though, stuck with Newton's system for a long time, which some historians argue actually held back British math for a while.
Interesting. But his mathematical genius wasn't just calculus, was it? He made big contributions elsewhere too.
Oh, absolutely. He found powerful new ways to work with equations and series. For instance, he developed something called the generalized binomial theorem. Basically, it let him expand expressions with powers that weren't just simple whole numbers, like fractional or negative powers.
Okay. Why was that so useful?
Because it allowed him to represent really complicated functions as infinite sums, like an endless list of simpler terms added together. And those infinite sums were much easier to handle using his new calculus tools, especially for things like finding areas.
Ah, I see. Breaking down complex math into simpler, kind of infinite pieces.
You could put it that way, yeah. He also did significant work in algebra, finding relationships between the solutions or roots of an equation and its coefficients. And in geometry, he took on this huge task of classifying all the different shapes you could get from third-degree equations, cubic curves. He grouped them into, I think, 72 distinct types based on their form, really foundational work in algebraic geometry.
And he had a method for finding approximate answers to equations too.
That's right, an early version of what we now call the Newton-Raphson method. It's a numerical technique. You start with a rough guess for a solution, and then you use calculus, specifically tangent lines, to make better and better guesses until you get really close to the actual answer. It's still fundamental in computer algorithms today for solving equations. He also tackled some incredibly tough problems that basically opened up new areas of math, like figuring out the exact shape an object should have to experience the least resistance when moving through a fluid. That was a first.
Wow, the sheer breadth of his mathematical thinking is just incredible. And all this math then paved the way for his even more famous work in physics, particularly in his masterpiece, the Principia.
Philosophiae Naturalis Principia Mathematica.
Yeah.
Published in 1687, often called the single most important science book ever written. It just laid out this comprehensive mathematical framework for how the physical universe works.
And it famously starts with his 3 laws of motion, presented as fundamental axioms. Let's try to make these super simple, maybe with everyday examples. The first law, inertia.
Right. Law 1, inertia. Basically, an object will just stay put or keep moving in a straight line at a steady speed unless some force acts on it. Think about leaving your keys on the table. They stay there unless you pick them up, right?
Huh?
Or if you slide a hockey puck across perfectly smooth ice, ideally it would just keep going forever. And if you're in a car that suddenly brakes, your body keeps wanting to move forward. That's inertia resisting the change.
Okay, got it. Law 2. This is the one often boiled down to FMA, right?
Why?
Force equals mass times acceleration.
Yes. That's the neat modern formula, though Newton stated it slightly differently, more about change in momentum. But the core idea is, when you apply a force to an object, you change its motion. You make it accelerate. How much it accelerates depends on how much force you use and how heavy the object is. Push a light shopping cart gently, it speeds up slowly. Push it hard, it speeds up quickly. Push a really heavy cart with the same force, it accelerates less.
Makes sense.
Yeah.
Then law 3. Action-reaction.
Law 3. For every action, there's an equal and opposite reaction. If you push against a wall, the wall pushes back on you with exactly the same force. When you jump up, you push down hard on the ground, and the ground pushes back up on you, propelling you upwards. When you step off a skateboard, you push it back as it pushes you forward. These three laws together created a complete system for analyzing motion.
And built upon these laws is probably his most famous achievement from the Principia, the law of universal gravitation.
Ah, yes, the big one. And let's tackle the apple story straight away. The apple almost certainly didn't hit him on the head. That part seems to be a later embellishment, a myth. But seeing an apple fall from a tree on his farm did apparently get him thinking very deeply about the force pulling it down.
And the incredible leap of insight was...
The stroke of genius was realizing that the very same force pulling the apple down to Earth was the force keeping the moon circling the Earth and the planets orbiting the sun. It wasn't different forces for heavens and earth. It was one single universal force acting everywhere.
Wow. Connecting the everyday falling apple to the moon's path? So what does the law itself actually state?
Simply put, it states that every particle of matter in the universe attracts every other particle. The strength of that attraction depends on two things. Their masses, more massive objects pull harder, and the distance between them. The force gets weaker the further apart they are. Specifically, it decreases with the square of the distance. So double the distance, the force drops to a quarter. FGM1M1F2R2 is the formula.
And this one single law explained so much.
It was incredibly unifying. It explained why planets move in ellipses, just as Kepler had observed. It explained the tides caused mainly by the moon's gravity pulling on Earth's oceans. It explained the paths of comets, allowing Halley to predict the return of his comet. It even explained subtle things like the slow wobble of the Earth's axis. He could predict celestial movements with amazing accuracy.
But that idea of a force acting across empty space action at a distance, that must have been puzzling for people then.
Oh, definitely. It was mysterious. How could the sun pull on the Earth with nothing physical connecting them? Newton was actually quite careful about this. He famously stated, hypotheses non fingo, which translates roughly to, I frame no hypotheses, or I don't feign hypotheses. He didn't claim to know the underlying cause of gravity, how it actually worked. But he showed mathematically what it did and how to calculate its effects precisely. And for his system of natural philosophy, that was enough.
Okay, so from the vastness of space and gravity, he also turned his incredible mind to the nature of light. This was detailed in his book Optics, which came out much later, 1704, and it was more experimental than the Principia.
Yes, Optics is a beautiful record of his meticulous experiments with light and color. It completely overturned the existing understanding. Most people at the time thought white light was pure, fundamental, and colors were somehow modifications of it.
And what did he discover with his famous prism experiments?
He showed definitively that ordinary white sunlight is actually a mixture of all the colors of the rainbow. When he passed a beam of sunlight through a prism, it spread out into a spectrum: red, orange, yellow, green, blue, violet. Why? Because the prism bends different colors by slightly different amounts.
And he proved this wasn't the prism creating the colors.
Exactly. He performed what he called the experimentum crucis, the crucial experiment. He'd use one prism to create the spectrum, then use a screen with a slit to isolate just one color, say red. Then he'd pass only that red light through a second prism. What happened? The second prism bent the red light, but it didn't spread it out further or change its color. It stayed red. This proved the colors were inherent properties of the light itself, merely separated by the prism due to the different refrangibility or bendability.
So the color is in the light ray, not made by the prism. Got it.
Precisely. This led him to organize colors systematically, creating the first color circle to show how they relate and mix. He developed a theory that light was made of tiny particles, or corpuscles, which explained reflection and why light travels in straight lines very well. Though, interestingly, being such a careful observer, he also noted phenomena that seemed more wave-like, such as the colored rings you see when two pieces of glass are pressed closely together, what we now call Newton's rings.
And his work on how lenses bend colors differently actually led him to invent a crucial tool for astronomers, didn't it?
It did. Traditional telescopes use lenses to focus light, but because lenses bend different colors slightly differently, they produced images with annoying colored fringes, chromatic aberration. To get around this, in 1668, Newton designed and built the first practical reflecting telescope. Instead of lenses, it used a curved mirror to gather and focus light. Mirrors reflect all colors equally, so there's no color distortion. His design, the Newtonian reflector, was revolutionary and became the basis for most large astronomical telescopes ever since.
Amazing. His optics also famously ends with those speculative queries, right?
Yes, a series of fascinating questions at the end of the book. They went way beyond just optics. He mused about the nature of matter, the cause of gravity, heat, chemical reactions, even touching on theological ideas about God and the universe. These queries were incredibly stimulating for future generations of scientists, hinting at concepts and research directions that would be fully explored for centuries.
It really drives home how his mind just didn't fit neatly into one box. Which leads us to his broader legacy, maybe. He didn't just make discoveries. He fundamentally changed how science was done, didn't he?
Absolutely. His rules of reasoning in philosophy, laid out in the Principia, were hugely influential. They emphasized basing theories firmly on empirical evidence, on observations and experiments, and using inductive reasoning while avoiding purely speculative hypotheses. He really grounded science and observation combined with rigorous mathematical deduction. That became the model.
And you mentioned some of his ideas even hinted at future fields.
That's right. Looking back, you can see seeds of later developments. For example, in the way he carefully handled his experimental data, trying to average measurements. Consider errors. Some see that as containing rudimentary ideas of data analysis or statistics. And his geometric way of treating physical quantities like force and velocity, using arrows basically, showing magnitude and direction, that contained the early essence of what would later become vector analysis.
His influence is just immense. Newtonian physics dominated for centuries and is still absolutely essential today for most everyday applications. Calculus provided the indispensable mathematical tools across science and engineering, and his books, Principia and Optics, they just established the standard for mathematical and experimental science.
It's truly hard to overstate his impact. He built the fundamental framework that generations of scientists worked within, elaborated on, and eventually, in some areas, extended or replaced, but always building on his foundation.
Now, the man himself, we touched on this, but he was complex. Sources paint him as secretive, maybe solitary, but also incredibly stubborn and fiercely competitive.
He definitely could be all of those things. His disputes were legendary. With Robert Hooke over ideas about optics and gravity, and of course that long, incredibly bitter battle with Leibniz over who invented calculus first. These show a man who passionately, maybe even ruthlessly, defended his work and his priority. Especially later in life, as president of the Royal Society, he wielded considerable power and wasn't afraid to use it to, well, support his own side or sideline rivals.
That intensity seems to have been legendary, too. Didn't his servant describe him forgetting to eat or sleep?
Yes, his longtime assistant, Humphrey Newton, painted this picture of almost obsessive focus. Newton would be deep in his studies, and this included extensive, often secretive experiments in alchemy, and would apparently completely forget about meals, sometimes staying up for days on end, lost in thought or experimentation.
Right, alchemy. It's fascinating that his interests weren't just limited to what we'd now strictly call physics and math.
Not at all. He devoted enormous amounts of time and energy to alchemy. It wasn't just about turning lead into gold, though that was part of the tradition. For Newton, it seems, it was a deeper quest to understand the fundamental principles of matter and transformation, searching for an active spirit or force in nature. He believed it was connected to how God had composed the world. And alongside that, he was deeply invested in studying biblical prophecy and chronology. He spent years trying to interpret scripture, calculate dates of ancient events, even reconstruct the layout of Solomon's temple, believing these held keys to understanding God's plan and the structure of the cosmos.
So for him, his scientific work and his theological, or let's say more esoteric studies, they weren't separate.
No, they seem to have been part of the same grand project. To understand the rational, intricate, law-governed universe that he believed a divine intelligence God had created. The laws he discovered in nature were, for him, evidence of that divine design.
What about his later life, after the major scientific breakthroughs?
He eventually moved away from Cambridge, took on significant public roles in London. He became warden and then master of the Royal Mint. And surprisingly, perhaps, he proved to be a highly efficient and rather ruthless administrator. He cracked down hard on counterfeiters and oversaw a major reform of England's currency. Despite achieving immense fame, he was knighted by Queen Anne in 1705. Sir Isaac Newton, he was often described as somewhat remote, perhaps unhappy, living more among his books and calculations than forming close human bonds. There is also evidence he suffered a significant nervous breakdown around 1693, perhaps related to exhaustion, intellectual pressure, or maybe even mercury poisoning from his alchemy experiments. It gives a glimpse into the immense strain he was under.
He really was at the absolute center of the scientific world then, interacting and often clashing with figures like Hooke, Leibniz, and the astronomer royal John Flamsteed, whom he also had serious disagreements with over access to astronomical data.
He was the dominant figure, no question.
Yeah.
And he shaped that world through both his sheer intellectual brilliance and his formidable, sometimes difficult personality and will.
It makes that famous epitaph written by the poet Alexander Pope feel so apt. Nature and nature's laws lay hid in night. God said, "Let Newton be," and all was light.
It's a perfect encapsulation of the transformative impact he had. As the great 20th century astrophysicist Subramanian Chandrasekhar once said, reflecting on Newton's achievements, "Every time I look at what Newton, I feel like a schoolboy admonished by his master, just sheer awe." Yet Newton himself, looking back near the end of his life, had that famously humble reflection. He said he felt like a boy playing on the seashore, and diverting myself in, now and then finding a smoother pebble or a prettier shell than ordinary, whilst the great ocean of truth lay all undiscovered before me.
That image is incredible. The vast, undiscovered ocean, especially coming from someone who revealed so much.
It speaks volumes, doesn't it? Maybe it's the humility that comes with true genius, recognizing just how much more there always is to know.
Well, reflecting on this deep dive, it's just so clear that Newton didn't merely contribute to science. He fundamentally helped launch the scientific revolution as we know it. He gave us the tools, the framework, the laws to understand the world around us, from, the smallest interactions right up to the grand clockwork of the cosmos.
His unique blend of penetrating mathematical insight, meticulous observation, and rigorous experimentation set a completely new standard for scientific inquiry, a standard that, in many ways, continues to guide us today.
And we really hope this exploration into his life, his mind, his discoveries has been both accessible and fascinating for you listening. This deep dive was brought to you by The Language Year, a channel dedicated to providing comprehensible input for language learners, but really for anyone who's just curious about the world and the incredible stories woven into its history.
Absolutely. Keep that curiosity alive. There's always more to discover out there.
Thank you so much for joining us on this deep dive. We invite you to keep learning and exploring right alongside us.
Goodbye for now.
Bye, everyone.